highly conductive channel, and the electrons can now very quickly flow from this channel to the ground. And that starts first right here at the surface of the Earth. That's where the electrons will first go to the Earth, and then successively electrons which are higher up in the channel will make it down to the Earth. And so you're going to see electrons going through the channel to the Earth, but first the electrons are closer to the Earth, then the electrons farther away, and then even farther away. And this is actually where most of the action occurs. The current is now enormously high, 10,000 to some 100,000 amperes, and you heat the air, you get a tremendous amount of light, the ions recombine, and you get pressure, heat produces pressure, and there comes your thunder. And so most of the action is not in the step leader, but is in this second phenomenon which we call the return stroke, which is from the Earth to the cloud. And the speed of that return stroke is about 10 to 20% of the speed of light. During the return stroke, there is about 5 Coulomb exchange between the cloud and the Earth, and 5 Coulomb is a sizable fraction of the total charge that was on the cloud to start with. After a return stroke, maybe 20 milliseconds later, this whole process can start again. You can get a step leader, and you can get the return stroke. However, the step leader will now follow exactly the same path that was made before, because that's where the air is ionized, so that's where the conductivity is very high. So that's the easiest way to go. And this process can recur 5, 10, maybe 15 times. So what appears to you as one lightning bolt, in fact, could be 10 flashes back and forth between the cloud and the Earth. And the real light is not in the step leader, that's very little light, but the real light is in the return strokes. So 10 return strokes, which may be 20, 30, 40 milliseconds apart, appear to you and to me only as one flash, which would take place maybe in as little as a tenth of a second. And during these 5 or 10 return strokes, you exchange between the cloud and the Earth maybe a total of 25 to 50 Coulomb, and that of course will lower the potential difference. And if the potential difference becomes too low, then the process stops. You have to wait now for the cloud to charge up again, and then lightning will strike again. And that can take anywhere from maybe 4, 5, 10, 20 seconds. And then you get another lightning bolt. The study of this process, of the step leader and of the return stroke, can be done with a camera which is called the Boyer's camera. Let me first explain to you in detail, in principle, how it works. If this is the area on the film that is exposed by your lens, suppose that I move the film at a very high speed to the left, and suppose the step leader comes down, and I see some light from the step leader, then I may see on the film this, some light. And from here to here would then be the 5 milliseconds which it takes the step leader to go from the cloud to the Earth. Now the return stroke takes place with a way higher speed, and so I see a tremendous amount of light because there's a lot of light in the return stroke, and of course this is very steep because it goes 100 times faster up than the step leader came down. And so you can measure these times, and so you can get the speed of the return stroke. And then later in time, maybe 30, 40 seconds later on the film, you may see another return stroke, and you may see another one. And so you can see then how long the time was between the return strokes, and you can also calculate their speeds. With the real camera, it's not really the film that is moving, but it is the lens that is moving. And the way these pictures are taken, and I will show you one, is if this is the photographic plate, then it is the camera that moves over the plate with a very high speed, about 3,000 revolutions per minute. And so you would get this information then not horizontally, but you get it spread out over the film. But you get the same information, you can calculate speeds and times. During the past decade, new forms of lightning have been discovered which occur way above the clouds, way higher up. Red colors have been seen, red sprites they are called, and also blue jets. The light is very faint, and it occurs only for a very short amount of time. It's very difficult to photograph. I have not been able to get good slides for today. However, I did see some pictures on the web, and when you log into the web, when you visit the web 802, which you should, then I give you directions how to access slides, pictures of the red sprites and of the blue jets. The physics of that is not very well understood. It's being researched very heavily. But it's way above the cloud. There are also other forms of electric breakdown, of discharge. They are different in the sense that it's not an individual spark, but there is a continuous flow of charge. It occurs always from very sharp points, so there is a continuous current actually going on. And some of that you may have seen, but you may not remember. When we used the carbon arc here, we had two carbon arcs, two carbon rods, and we had a potential difference between them, and we got a discharge between them which caused a tremendous amount of light, which we used for projection purposes. So a carbon arc discharge is such a form of discharge whereby you have a continuous current. It's not just sparks. If you take grass or trees or brushes for that matter, where there is thunderstorm activity, they can go into this discharge at their sharp tips. And we call this brush discharge. We call it St. Elmo's fire. It's all the same thing. It's also called corona discharge. I normally call it corona discharge. It produces light because the ions, when they neutralize, produce light. Heat makes sound, pressure, and so you can hear this cracking noise of the corona discharges. An airplane that flies or a car that drives, there's friction with the air, and any form of friction can charge things up. And so it's not uncommon at night that you can see this corona discharge from the tip of the wings of an airplane. I've also seen it from cars, corona discharge from cars, which charge themselves up simply by driving through the air. The airflow would charge them up. You can hear it, cracking, and you can see it sometimes. If it's dark enough, you see some light. In general, it's bluish light. Something completely on the side, going back to the lightning bolts. Lightning bolts, the discharge, the moving electrons can cause radio waves. And these radio waves you can receive on your car radio. And all of you have experienced this. Driving around, lightning very far away, you can hear it on the radio. So that's telling you that there is lightning going on somewhere. After a thunderstorm, something that many of you may not have experienced, because in the cities there's always exhaust from cars that spoils everything. But when you're out in the country, after a thunderstorm, there's a very special smell in the air. I love it. And that's ozone. Oxygen 2 in lightning becomes oxygen 3. And oxygen 3 has a wonderful smell. And you can really smell that. It's very